Okay, g'day everyone.
G'day. So I'm delighted to be here speaking to you on this lovely Sydney winter afternoon, and I've got you for the next hour and a half, I think, and I'm going to present a talk on photonic circuits for the new information age, faster, smaller and greener, and this will all start to make sense. My talk is a mixture of a bit of historical perspective, global context, frontiers of science, some of the work we're doing here in the University of Sydney, in the School of Physics. I'd love to have some questions along the way. I think we've got an hour and a half including questions, so one question every 15 minutes is probably okay, and if I don't get a question, I might start asking you questions. So that'll get you engaged and interested. So as Chris said, I'm the director of CUDOS. It stands for Centre for Ultra-High Bandwidth Devices for Optical Systems. It's a bit of a mouthful, but we are Australia's Centre of Excellence in Photonics. Headquartered in the School of Physics. We've been here for 8 years and we've just received from the federal government funding for another 7 years. So let's go forward. Okay, what happened? Didn't. After all of that, no connection. So let me start off at the beginning. And you're all bright students and you know something about basic physics, and I'll remind you that photonics deals with the electromagnetic spectrum. So when we talk about photonics, we're looking at light. Light is an electromagnetic wave, and of course the electromagnetic spectrum spans all the way from gamma rays, ultraviolet light, and we have this very narrow region here that's the visible spectrum that we can see. To the long wavelength side of that is the infrared, and it turns out in communication systems we use the near infrared, and then you get microwave frequencies. The mobile phone network is based on radio frequencies, and that's as far as we really think about it. But this is all the electromagnetic spectrum, and so many of the ideas that I talk about today, the initial breakthroughs are often in the microwave region because it's easier to work at that wavelength range, but it's the same principle, the same equations. So, having set everything up, my little connection is not working. Oh, look at that. Technology. If it was only a photonic technology, this has just died on me. What can I say? So photonics is the science and technology of generating, controlling and detecting photons. Photons are the building blocks of light, and it began with the invention of the laser 50 years ago. And in fact, last year we celebrated the anniversary of the laser. So photonics is, underpins a number of very important areas of society. I was in Taiwan last week, and someone said to me in Taiwan, they said, did you know that Taiwan has a $50 billion industry in photonics? And I had to stop and think, and what are they talking about? Well, they're talking about the display industry. That's photonics. That's all based on laser technology, optics. But of course, it is also key to storage. Inside your discs is a laser. Broadband access, information. Photonics is used in microscopes, in the health sciences, and even in astronomy. So all of the research that I'm talking about today, in fact, is relevant to these different areas, but I'm going to focus on communications because it's really an easy one to explain and critically important to all of us. Let's go. So let me give you the punchline up front. I'm going to give you the big message up front, and then I'm going to take you on a journey that will look at a number of different important themes. But what we're looking at is today's global optical fibre network. In fact, this is about 5 years old. It shows you the optical fibre that's been laid under the oceans connecting the world. Okay, there are literally tens of thousands, hundreds of thousands of kilometres of optical fibre lying at the bottom of the ocean connecting the major cities of the world. These are the pipes, the freeways, if you like, that forms the backbone of the internet. So the freeway analogy is actually a good one, and if I take you along that a little bit further, it's worth recognising that analogy. And I like to say that the communications network is just like a freeway network. We've got these massive pipes that link the cities that are the transport network, the transport highways for the data. But then we've got these junctions or routers where we've got to get data on and off these freeways. And so this is really the grand challenge that our research is dealing with, and my talk is going to focus on, is getting light onto the freeway, getting light off the freeway, doing that efficiently, doing that with nanotechnology, with low energy consumption, and avoiding this very simple sort of scenario, which is really the bottleneck that communication networks are facing. So to give you the punchline up front, our research is all about photonics enabling more bandwidth, and what we've been working towards for the last 5 years is summarised in this simple cartoon, and I'm going to expand on this and take you on a journey over the next hour that will explain all of the different sort of concepts here. But we're talking about a revolution that's going to replace these large electrical switches that are very expensive. If you ever go to one of Telstra's exchanges, they have these massive facilities that are electronic systems that process all the data. They consume vast amounts of energy. I'm going to give you some really concrete examples of this. They generate heat, they need air conditioning units. Most of the space is in fact cooling, and they're low bandwidth. So the revolution that I'm talking about is optics on a chip. Can we do the signal processing on a chip using optics? Let's face it, we're already using optics and photonics when we send the data under the oceans through the optical fibre. Can we do the signal processing on the chip without going into the electrical domain? So if you walk away from this talk now, you've already got the punchline. You already understand where we're going, what it's all about. So let me now take you on further. This is going to become frustrating because I keep on clicking that, expecting the slide to change. So it's similar to the revolution that we've seen in microelectronics with the invention of the transistor 50 years ago, thereabouts, and the incredible development that has gone on in that field, leading to the world that we live in today, where I can't get out of bed with my BlackBerry. I don't know about you, you've all probably got iPhones and smartphones and these amazing devices that build on this incredible advance and progress in microelectronics and now nanoelectronics. So we've seen an evolution from what you see on the left-hand side, and this is a photo taken, I believe, from IBM, but it's probably similar to what you would have seen in labs all around the world, including at the University of Sydney back in the early days of computing, to today where we have the the iMac? This is obviously a few years old because this type of performance now sits inside your iPad or your iPhone. So this is what our photonic integrated circuit's going to look like. And because I know it's afternoon and you've all had a nice warm lunch and probably a little bit sleepy, this is a bit of a cartoon explanation of what I'm talking about. So you're looking now at a simulation. This is not real world. This is what you might see if you look through a microscope. And I think some of you have been in the CUDOS labs this week and you may have looked through a microscope at one of our chips. this is roughly speaking what it looks like. So let me take you through. You've got optical fibre here, you've got optical fibres here, and what you see here is a packet of data. The little bright spots aren't photons. That is in fact a pulse of light made up of hundreds of photons, and you can see what's going on here. So the light enters the chip and there are a number of different functions. So let's look at a spectrum analyzer. What a spectrum analyzer does is it takes white light and splits it up into its different colours. Here it's made up of little tiny holes. Remember, because we'll come back to this concept later on, this is a photonic crystal. I think you can see what's going on there. The light's dispersed into the different frequency components, and that's incredibly important in communications because we rely on different colours to encode different channels. What else can we do? Well, for many years we've worked towards an optical buffer. A buffer is, as it suggests, a device that slows light down. We can do this in photonic structures. Can you see these pulses are slowing down? You'll notice also as these pulses slow down, something else is happening. They broaden out, they disperse, and we've got a bit of a problem here because they start to interfere with each other. I'm going to come back to that example later on, so do remember that as well. Let me zoom out and let's see if there's anything else we can look at. Well, we can do other very sophisticated things on this chip, such as change the wavelength of light. So this is a cartoon, but this is done routinely now. So we can see a little device on our chip, red light comes in, this is a laser beam, there's an interaction on this chip through nonlinear optics, and what we see coming out of this chip is green light. So I've started to give you a little bit of a feeling or a flavour for where we're going now. Let's go on a bit further on this journey. Now the wonderfully exciting thing is that the photonic integrated circuit that I'm going to talk about, and I've got one here, I'm going to hand this out in about 5 minutes. We're going to make this circuit using the same technology that we use in microelectronics. We're going to use the same lithographic techniques that are used in the industry to make these devices. Okay. Now, I've given you that preamble. Let me go back now, bit of history. What is it all about? It's all about communicating. It's all about communications. And of course, we have been communicating for hundreds of years, thousands of years. And I like to use this example. The semaphore. This is back in Napoleon's day. And the semaphore was one of the very first long-haul optical communication systems. And it was very effective, but the bit rate was reasonably low. Now again, because it's early afternoon, and I know you're all tired, I've got a little bit of entertainment for you, a little bit of a short movie. Let's see if this works. The background is that, well, let's tell you the background after the movie. I'll let you watch this.
I am not wearing anything either. Ah, Mr. Jim, if only we had.
You might recognise where that was filmed. That was, they were my students, and it was actually prepared for an after-dinner speech that I gave about 5 or 6 years ago at a dinner in honour of Harry Messel. And I had been overseas for a few weeks and I asked them to do something magic for me, so I've got some good material. So that was filmed on the roof, and the student's gone on to be a very successful entrepreneur. Anyway, so we've seen through history this revolution in communications. It took a while, so we had the Pony Express for many years was really leading edge technology. This was as good as it gets. Things started to get better, and we had the invention of the telephone, which obviously revolutionized the world. And today we live in a completely different world to your parents' generation, and I think even my generation, to be honest. I mean, how many of you are not on Facebook? Ooh. Harry's hand didn't go up. Yep, nods with great enthusiasm. So we're living in this amazing world now where the internet is part of everyday life for social networking, but it also is critically important to areas banking, education, health, defence and so forth. I was in China last week, and of course they don't have Facebook. They have their own version. They don't have YouTube, but they have something else. There are already almost 2/3 of a billion people signed up with Facebook. So it's just tremendous progress, and what we're seeing at the same time is that if we look at the growth in internet traffic, this is from Intel, and it plots in exabytes per month, the increase in internet traffic. Now, the absolute scale here is not that important. What is important is that it's basically doubling almost every 2 years. Okay, the bandwidth in the core of the network is doubling every 2 years, and it has been doing that for as long as there has been a network. It's not slowing down. There's no evidence that it is going to slow down. And in fact, my colleague, Professor Alan Wilner at the University of Southern California, was in Sydney a few years ago, and he gave a wonderful presentation, and he talked about, well, what's the absolute upper bound? When will it slow down? How much bandwidth can the human absorb usefully? And the number is something like 50 gigabits per second, which means at this rate there's another 20 years, 30 years before it's maybe going to slow down, but even then something else will come up that we haven't thought about. In Australia we have a company that's building a national broadband network, and Photonics is the key technology. So this is a network, and many of you will know about this because it's one of the most popular topics in the media. It hasn't been recently, but for a long time this was a very popular topic for the media, but not necessarily a popular topic for the people on the streets and for the politicians. So the government announced a $43 billion project a few years ago to build a national broadband network that will provide every Australian with, well, 95% of Australians at least, 1 gigabit per second. So that's, how many bits is that? That's 1,000 megabits per second of data for every home, essentially. And for those that are not on the optical fibre grid, wireless or satellite will give them 50 megabits per second. So this is a map of Australia, and you can see the type of topology that we might imagine with this rollout of fibre to the home for 95% of the population. This is a very exciting project. It puts Australia in the lead if we can actually build it. Let's hope they can actually do it. If it doesn't get derailed, it's a magnificent project. It will grow the economy, it will stimulate innovation, it will transform healthcare, education and so forth. It's probably Australia's biggest infrastructure project ever. So no matter what side of politics you sit on, I think you have to agree this is a very exciting and very important project. So far what they've been talking about is fibre to the home, getting the data into the home. there hasn't been a lot of consideration to what's going to happen now between the cities. How do we get all the data between the cities? How do we get the data from Sydney to the US? And it's going to need a complete rethink on the backbone of the network. So there are some real challenges that university researchers and industry are facing. There are some other very fascinating sort of contextual statements and facts that I'd like to make. All of these data centers, Google, Facebook, require these big data centers, something that didn't exist 5 years ago. Where do you think all the data sits and is stored and processed? Well, if you talk to Facebook, they will say, well, we had a data center in the middle of Los Angeles, but it was too expensive because the power bill itself was huge and we needed water. So we moved next to a power station on a river so they could get cheap power. So these data centers are enormous. They're the size of the School of Physics. Literally hundreds of thousands of computers, huge amounts of data that's been stored and processed, very expensive, and it turns out consumes significant amount of energy. Okay, a lot of energy. Most of their budget is in the power bill. And I'm going to come back to this example in a few slides to make this really concrete. So now there's an emerging theme that says, okay, not only do we need more bandwidth, but we have to give some consideration to the energy associated with all of the data processing. So this is a slide that often gets people, confronts people. It's a busy slide, so bear with me. It's from my colleagues in Japan, the National Lab AIST, which is in Tsukuba, just north of Tokyo. And what it plots on the right-hand side is total internet traffic for Japan. The left-hand side is the annual energy consumption of IP routers. These are pretty straightforward concepts. You can see that the internet traffic is growing and it continues to grow, nothing too surprising. Doubling roughly every 2 years, as I said. This curve, however, shows you that the energy consumption increases at the same rate as the data traffic. Right now, it's only down at about maybe 3%. This one here. We're down at a few percent of, so 2010's here. We're down at a few percent of Japan's total energy budget. So a few percent of Japan's total energy budget is in the internet. And you say, a few percent. That's more than the airline industry. Okay? But more frightening is that it's increasing at the same rate. This line here is Japan's total electricity generation. So if nothing changes, if we continue to go on at the current pace without innovating, without changing the way we process data, there's a looming crisis, and it's only a decade away. Now this slide is particularly dramatic because it's been prepared by my good friends in Tsukuba, and I was having dinner with this gentleman last week, Shunamiki, and he's telling me, well, we don't get power all day now because they've had this massive crisis, of course, with the tsunami, and their power stations have basically been cut down a notch. So I think this puts it all in context, and it says it's not just about more Facebook. We've got a looming environmental crisis if we don't do anything. And I'm expecting a question pretty soon. Okay, yes?
Well, don't the lasers used in optical fibers consume as much energy?
So that's a good question, though. The lasers consume as much energy. So it's a very complicated problem to actually identify where energy is consumed. How can we save energy? Turns out the lasers are a very small part of the equation. The lasers consume only a very small amount of energy. There's energy consumed primarily in the routers, the switches, the air conditioning units that cool the switches and routers. I mean, let's face it, at the moment, there's more energy consumed by your plasma TV in your bedroom, probably, than the energy that you're consuming in the internet. At the moment, the situation's okay, but as this internet traffic grows and grows, it's going to become a problem, and it's not the lasers, my friend, at all. But good question. Want to see a question every 10, 15 minutes. Now, there's another exciting context, and this is going to highlight the role of nanotechnology, and I'm going to come back to this in the last part of the talk, and that is the use of photonics in computers, not to do logic. We're not going to use photons to do logic. That will never happen. Electronics is certainly better for doing sequential logic. Photonics is better for doing signal processing, which means only a few logic steps. We can do much faster, more energy efficient on a few logic steps. But in the context of computing, what we're starting to look at from companies like Intel, IBM, is this idea that we're going to have connections, photonic transport, optical communication links on the motherboard, within the computer, or even on the chip. Okay, and this is one of the big bottlenecks the electronics industry is facing, communications within the computer, within the motherboard, on the chip itself. And as I'll show you, it turns out that silicon, which has been the backbone of microelectronics for 50 years, is actually very good for photonics. And so there's been amazing progress around the world in building photonic circuits on these microchips. Here's a simple example. You just link two computers with an optical fiber. Okay, this is already happening. And for example, this is a beautiful example from Intel and the very famous Mario Panaccio, who was an Intel fellow and director of Intel's Photonics Technology Lab. They released a breakthrough about a year ago that simply used a silicon photonic transmitter chip with silicon lasers and modulators to communicate between computers. So this is a very simple example of photonics being used in the computer industry. Rather than an electrical connection between computers, here you've got at the side of the computer a little chip that plugs in, and there's a laser modulating data, injecting onto an optical fiber, send it across the room, take advantage of the beautiful properties of glass and the bandwidth that you have to another chip where you can detect and then convert that back into electronics. So another big sort of slide to remind everyone what it's all about. Smaller, faster, greener. This is a typical router or communications hub that you might see at Telstra or Optus or anywhere around the world. A lot of high-speed electronics, a lot of sophisticated computing. Photonics is not going to replace all of it, but what we're hoping to do is to replace some of it, miniaturize it down onto a chip, an optical chip. Reduce the footprint, increase the speed, the bandwidth using nonlinear optics, and I'm going to explain what nonlinear optics is all about, and reduce energy consumption. So, why can't we do it right now? Yes?
With the network problem, surely part of the problem is that they've got to use lots of chips for these supercomputers that they're using. So surely just by changing the connections within those chips, you can actually increase the size that much.
What's the question? Surely we can...
The question is changing how the overall the chips are connected together is going to change the size even if you've still got loads and loads of chips.
And you're still using lots of chips, so you're still going to have really, really big machines, even if you're connecting them with optics.
You've still got lots of chips. In the context of computing, what you're trying to do, within a computer you have all of the processing, but you have also communications going on within a computer. Okay, right now in my laptop there's a vast amount, there's a communication network within my computer, and it's all electrical, and it's slow, and it's not fast enough. and it's generating heat. And so whatever architecture you're going to imagine for the next generation of computers, I want to replace that communications with light. I want to use optical wires. I've got more bandwidth. I don't generate any heat. It's faster, it's greener. Yes?
Given that electronic processing is significantly slower than optics, as you just said, wouldn't connecting processes by optics be like connecting a freeway to a one-way street? And that you sort of have some lag involving because you have really fast transfer of data and then really slow processing?
Well, yes, I think the point is that it's an interesting, you're using my analogy against me. Well, I guess what you've got going on is in the computer parallel processing with all of this different parallel processing that's churning away as fast as it can. And I want to get all of that data over here. And I can do that with lots of coaxial cable, lots of electrical wires, or I can take all of that different data, modulate lasers, and multiplex that onto one optical fibre. So the fibre is this massive freeway. I've got this massive freeway that has unlimited capacity for data. And I can take all of these little towns, all of these suburbs, all of these cities, take all of that data, put it on one freeway. At the moment, I've got all of these cities and towns, and I don't have any big freeways, so I've got a real problem. I've got a bottleneck. So I think I understand your confusion, and I think, did my comment help you?
It's more that once you've used the example of you've got, say, one, even on the chip, you've got sort of one processing area connected to another processing area by an optic fibre. So
But you may not have one, you may have dozens.
But you're going from your little town onto the freeway, but then when you get to the next processing chip, you're going back onto one tiny town, and that'll pull
Yes,
there.
but you may not go, you're not going to take everything into that town. You're going to demultiplex it again. So the freeway has loads of data, and I can send it over all sorts of different places. You're right. You're right. There's no point having a freeway that's got more, is faster than the electronics. That doesn't make any sense. You're right. So the freeway, I'm going to take all of that data, I'm going to spread it across all these different chips. Good question. Got it. Yes, quickly.
Very quickly, is there any place that I can get that DVD file? The really cool one with all the lights.
Talk to me later. So why is this a hard problem? We're talking about the photonic equivalent of an integrated circuit. But we really want a femtosecond optical response. So we want to be able to do things much faster than electronics. We want a circuit which is compatible with millimeter scale optical circuits. So I'm going to try to talk you through ultra-fast light-light interactions. This is one of the most difficult concepts you may come across this week. It's a hardcore physics. I'm going to try to bring it across in a simple way that doesn't patronize you but may bring you into the beautiful physics. We're going to talk about waveguides in nonlinear materials, and then if I have time, I'm going to talk about photonic crystals and slowing light down. So, a little bit of history. The laser was invented about 50 years ago. Mayman was working at Hughes Lab. Didn't win a Nobel Prize, should have. Demonstrated the first laser 51 years ago. Townes, Basov and Prokhorov received the Nobel Prize for their fundamental work leading to the construction of lasers. Townes and his student Jim Gordon, they're both alive and reasonably healthy. I see Charles Towne reasonably frequently, 95. Jim Gordon, I think 85, working at Columbia University. They made the first maser. Bloomberg and Sharlow received the Nobel Prize for their contribution to the development of laser spectroscopy. One application of this is nonlinear optics, which is when nonlinear optics, which means methods of influencing one light beam with another. Okay, so let me talk about that idea. How to interact one light beam with another, because photons, are they bosons or fermions? Which one? Harry. Ah, yeah. Anyone. Okay, you'll have to, that's homework. They don't interact with each other. So what is nonlinearity? It means that the output is a nonlinear function of the input. So a linear system is pretty straightforward. Well, what's a nonlinear system? It means there's an interaction. Just a simple example of a nonlinear interaction that you're all familiar with is this one. This is nonlinear optics. Well, this is nonlinear physics, nonlinear science. Okay, I'll take this a little bit further. Now, nonlinear physics is important across all disciplines. Mathematicians study this. It is important in applied physics, chemistry, life sciences, hydrodynamics, social sciences, solid state physics, and of course optics. Typical examples are shown here. Recently I've been involved in work looking at the nonlinear effects associated with rogue waves in the ocean. You might remember the movie about the big ship that was out in the middle of the ocean, and this wave appeared out of nowhere and knocked the ship over, and the ship sank, and they all survived underwater for a month. What was that movie called? Poseidon Adventure. That was a rogue wave. They don't understand where they come from. There is no model for rogue waves predicting them, but they're starting to realise that it's a nonlinear phenomena, and in fact that it has some very strong links with the nonlinear optical systems that we're involved in. So again, let me take you through this very simple story. Photons, whether they're fermions and bosons, that's your homework, don't interact. They don't interact. Two light beams in a vacuum, in general, don't interact with each other at all. So what's going on here? Why are we going to get a nonlinear interaction? Well, that's because the medium itself will allow these photons to interact. In other words, one laser beam, one light beam is going to change the medium, and the change in the medium is going to affect another light beam. Got it? Anyone not get that? You got it. So hence we can make photons interact, and we do it. That's nonlinear optics. Here we go. There we go. They're in love. And so nonlinear optics we see every day. For example, we focus sunlight down through a magnifying glass. That's nonlinear optics. Burning through paper, the light field is modifying the medium, and another light beam would have been affected by it. Now, what's happening at an atomic level is in fact more complicated, but without going into too much detail, for those in the audience with an inclination of physics, the light field interacts with the electron cloud. It distorts the electron cloud. So you can see the electron, you can see the light field, you can see the atom with the electron spinning around it. The light field distorts the electron cloud. This happens on a time scale of 10 femtoseconds, 10 times 10 to the minus 14 seconds. So that's a lot of zeros. That's faster than anything else that we deal with in life. It's about 1,000 times faster than the world's fastest electronic switch. Okay, so you're starting to see the science, the physics that we harness. So these nonlinear effects allow us to process information all optically. And this is where this big idea of all optical functionality comes from. Can we harness or exploit the optical nonlinearity, which is instantaneous effectively, to control information on a chip? The answer is yes, we can do it. But we need some pretty exotic materials. This is a busy slide. What I'm going to do is hand out, so it's a show and tell, a circuit. This is a photonic circuit. It's what you see on the slide that I'm going to explain in a minute. It's been fabricated by depositing a very special glass, chalcogenide glass. The details are not important, but this glass has a massive optical nonlinearity, thousands of times larger than optical nonlinearities in other materials. We've then used photolithography. Sounds like jargon, but that's just printing. We've printed a circuit. We've got strong nonlinearity, very small mode volume, low propagation loss. So this is what it looks like. The glass sits on silicon. The length scale, this is only about 2 microns. Okay, so this is about wavelength scale. The feature size that matters here is about 5 nanometers. And you can see the optical fibre coming in, you can see the optical fibre coming out. Now, I'm going to hand this around, don't touch it. You'll look at it and you'll see fingerprints on it. And you'll say, why is that? Because I was in Taiwan last week and I handed this circuit out to an audience just like you. They didn't speak good English, so they didn't hear me say, don't touch it. And you can see all these fingerprints all over, and I'm going to go and scan the fingerprints and I'll have it on record. So if you touch it, I will know who, you can see them all. So if you look under the light, you should see these wonderful little circuits that have been etched into this glass. Again, don't touch it.
You think he's kidding about the fingerprint? He's not kidding.
I will keep that on file. So these are the photonic circuits that CUDOS has been working on, and I'm going to give you a flavour over the next 20 minutes of some of the science and technology and beautiful physics that these circuits have been part of. But have a look at that. So this is another look. About 2 years ago we reported a paper at a conference that was the world record of demonstration that we could switch light 1 terabit per second. So that's 1 million times a million bits of information a second. So who wants to tell me how many DVDs is that? Yes. Sorry? Well, how many? Well, maybe you're right. You may know. How much is on a DVD? 4.7 gigabytes. So do your math again. Thank you. You literally got hundreds of DVDs now, and we use this simple chip, the chip that you're going to have a look at, to process, to switch data, essentially hundreds of DVDs a second. Okay, very exciting breakthrough. We were picked up by all of the media outlets. In fact, they ran a story in the Sydney Morning Herald on the Monday, and it was embedded in a bigger story about the release of the iPhone. Okay, big story about the iPhone. Right in the middle of was this Sydney University breakthrough, terabit per second. No, it didn't say a terabit per second, it said a megabit per second. The journalists had got mixed up and reported this as the megabit per second switch. The funny thing is nobody noticed. Only by a factor of 1 million. But we were picked up by all the major media outlets, and Catalyst, which is Australia's premier science documentary series, did a story in 2009, a wonderful story actually. Paul Willis, who's now in Adelaide, is the director of the Royal Institute.
Last night, he was the compere of the program last night.
He was a journalist, and he actually did a wonderful job, paleontologist background, so he's got no physics, but he explained this very well. And you can go online, you Google CUDOS, my name, and Catalyst. You'll see the story, and this is my team here and my colleagues, myself looking very professorial and wise in my office, talking about how this is transforming the world. So let me just give you a little bit more historical perspective. Some of you might know that in 2009, the Nobel Prize in Physics was awarded to Charles Cowell for the invention of optical fibres. This was somewhat surprising for the community because, of course, optical fibres are ubiquitous. Many of us had forgotten the history, but it turns out in the late 60s, before I had been presented to this world, this young scientist working in the UK sat down and he had the key insight that silica could be low loss enough for the transmission of data over reasonably long distances. And he wrote this up in a seminal paper, and he presented the first detailed measurements. It's amazing to go back and look at this publication, because he predicted that best case scenario, we might be able to transmit 100 megabits per second over a kilometre. So the record at the moment is 100 terabits per second over 100 kilometres. So it's amazing how much progress has been made. But anyway, he's a distinguished gentleman. He is retired and unfortunately had Alzheimer's, and so was not able to present at the Nobel Prize ceremony, but his wife did present in Sweden, and it was a very exciting time for the photonics community. But let me just talk a little bit about the history and try to give you some more context, because often people think it was all reasonably obvious. Surely this was just something that was inevitable. Someone else would have come up with this, but that's not true at all. Back in the 60s and the 70s, really we had no idea where this was going to go and which approach to take. Some of the first optical communication systems, you know, lamps and free space. And I can remember Bell Labs in New Jersey set these lamps up along the side of the freeway, lens guides and mirror guides and even gas lenses. And then, of course, we had the laser and we had optical fibres. But it took a long time, and I have a question from this guy here.
Sorry to keep disturbing you, but we were talking about the photon interactions with the electron density cloud a little earlier.
Yes.
And you said that the photon distorts the density cloud. And I was wondering, presumably that gives some potential energy to the electron relative to the nucleus, which could mean that it could just re-emit a photon rather than going on the appropriate nonlinear interaction. And presumably that has the consequence that, I'm not quite sure what scale we're talking about with photonics, but if it's on a very small scale, presumably that means you lose the information encoded in small batches of photons, or if it's on a very larger scale, you need to put photon multipliers in to recapture the data.
Stop. So it's a complicated interaction, but you certainly do not lose information. But what you do often see is when you go in with one frequency, this distortion, this nonlinear distortion will actually manifest in the light being emitted at a different frequency. So that's a distortion, if you like, isn't it? But it's a useful distortion. So the beautiful thing about nonlinear optics is we can control it to some extent. We can force it to do things such as shifting the frequency of light. Remember my cartoon, we went in with green and we came out with red. So that's a sort of a distortion, you could say, in your simple picture, but we're going to benefit from that in some very important ways. That's called frequency conversion. The reality is what goes on at the atomic level is very complicated. And the pictures that we use in our discussions is simple. You have to use a simple picture because the detailed description at an atomic level is very sophisticated and complicated, and simulations of these structures is requiring ab initio calculations. It's well beyond the scope of what we want to do. But the simple pictures work, and the nonlinear response is instantaneous. It's well understood, and there are textbooks written on this and have been for a long time. Good question. So what do these optical fibres look like? They're pretty simple. It's a strand of glass, pure glass, about 125 microns, with a core in the middle. The core has been doped to have a slightly higher refractive index, and the light is trapped by total internal reflection. The light simply bounces back and forth off this mirror and is trapped by total internal reflection. The glass is very pure. It's so pure that if I were to build a glass plane 50 kilometres thick, I could still see you through that glass. That's how pure the glass is. That's how low loss the glass is. Yes, sir?
I have a rather relatively basic question. If you bend an optical fiber, does the angle of the light inside change with respect to the surface, and therefore would you not have total internal?
Yes, good question. Yes, absolutely. So if you bend the fiber, at some point, the light is no longer going to be within this sort of cone of total internal reflection, and you get what's called, very technical term, bend loss. Okay? And indeed, that's a big issue. So these fibres, I was going to bring one down to the meeting. They sit on these spools that are about that diameter. Okay? And when they're sitting in the rack, they are typically in that diameter. And if you bend the fibre around your finger, indeed, you do get a lot of loss because of the bend loss. One of the recent breakthroughs that's come out of Corning in the US has been a very low bend loss fibre. And the context for that is data communications in the home. Really what they want is to build optical fibres that can basically be very simple, low cost, very easily manipulated, so that you could have it running around the floor, corners of the room, even in an automobile. So, and have no bend loss. And what they actually do, it's very clever, they put holes around the core. They put little air holes. So there's air, so the refractive index step is much larger, so you get stronger confinement, less bend loss. Yep, good question. So the communication systems look something like this. It's very simple. You have the freeway. You have now what we call wavelength division multiplexing. Rather than just encoding data on one wavelength channel, you have a bunch of different lasers at different wavelengths. And these are like the lanes of a freeway. I think that's a good analogy. These are like the different lanes of the freeway. We've been talking about changing the colours, haven't we? Changing the frequency of light. I think the analogy there again with freeways is important. When I drive to Canberra on the freeway, most of the way it's smooth sailing, but every time you get to a major intersection, I have to zip to the left and then zip to the right and then zip to the left, because there are cars coming on from Goulburn and so forth, and that's a real pain. So this frequency changing business is all about making the bandwidth transport more efficient, so we don't have that bottleneck. So changing lanes, that's what it's allowing us to do, change the lanes. It's interesting now to look at the spectrum. We talked about this at the beginning. Remember, the electromagnetic spectrum goes all the way from gamma UV up to microwave, and I said, well, in fact, the visible range is down at around 400 to 700 nanometers. And in optical fibres, we use a section of the freq bandwidth that's here. Very narrow part of the spectrum from 1.5 microns to 1.6 microns. Tiny slice of the spectrum. Okay? But the actual bandwidth that we have access to is about 25 terahertz, which is 25 terabit per second. The red curve, I will emphasise, is in fact the gain of an optical fibre amplifier. This was probably one of the top 5 breakthroughs of the 20th century inventions. The optical fibre amplifier that allows light to be amplified in the optical fibre itself. But we're still only using a narrow part of the optical spectrum. All right, let me have a drink, take a deep breath. We're in the final stretch. I'm going to talk about some of the new science now. I think I've motivated, explained communications, some of the bandwidth challenges. So we were talking before the seminar about nanophysics, nanoscience, and the nano-age. And so we've seen this evolution from the mechanical age, the electromechanical age, the electronic age, and I guess we're in the nano-age. Nano can mean different things to different people. So you probably heard at this school from biologists and material scientists giving you different angles on nano. We obviously think about nano-photonics. And if you've got that photonic circuit, where is it? Okay, good, don't touch it. So you're looking at a device that's based on nanophotonics. The waveguides, the wires on that chip are about 1 micron. The feature size, the dimension, the scale that we have to control the material is 10 nanometers. So this is a photonic nanowire. This is what you see, and the scale is not here. This is 1 micron. This is 1 micron. We get even more exotic structures. This is a photonic crystal structure. These holes are about 100 nanometers. This is a ring, okay? But it's only 2 microns across. The light comes up here and then rattles around in this ring. And I can make a storage device. You might have heard from Sir John Pendry. Were you all awake during his talk? Okay, well, he's an absolute legend, isn't he? I mean, we're expecting Nobel Prizes for John very soon. Wonderful speaker, absolute pioneer. And he has been developing these metamaterials, and it's a beautiful science and physics, and he has promoted the idea of optical cloaking, and he obviously talked about that during his seminar. This is work from Berkeley. This is an actual metamaterial. This is a nanostructure. These layers are about 100 nanometers apart. But you also have, believe it or not, 3-dimensional structures. So this is a 3-dimensional microchip. This is an artist's impression from Sajeev John, who was one of the pioneers of a 3-dimensional chip that can store light, can process light, and takes advantage of the 3rd dimension. These structures are incredibly difficult to make. Right at the front here, I'm going to show you some examples later on of what's been achieved. So there's a Moore's law for photonics. And Moore's law, let me just ask you, you've heard about Moore's law this week? Okay. So there's a Moore's law for photonic integration, and this slide kind of gives you a hint of what's been happening. You can see the scale there is years and integration density, and what we've seen over the last 20 years is a revolution as we get more and more sophisticated. We're getting to the point now where the elements that are defining the functions on our chips are on the scale of a wavelength. Mind you, that's still bigger than the scale that is in the transistors in electronics. And remember, we're not going to replace electronics. This is not about doing computing as such. So this is all part of a photonic integration revolution. I'll go through this quickly because we've covered it. We're only at the beginning, and the research that we're working on now is towards a revolutionary photonic integration platform that's going to have more functionality, as I've hinted at, low footprint in space and energy, and disruptive across all areas of science. I haven't got time. I could talk about the science we're doing in quantum information, using photons on a chip to do quantum computing. I could talk about the science we're doing in astronomy, using these chips for detection in astronomy. I can talk about how we're using these chips in environmental sensing, but I don't have time. Okay, the last topic, maybe possibly the most exciting one, the one that'll get most discussion, the topic of slow light. Now, what does Einstein say about the speed of light? One person, loud and clear. Say it again.
Constant.
No, what does it say? No, well, he says more than that. Constant in a vacuum.
Yes.
Okay, so the speed of light in a vacuum is 2.99 something. I was at a conference last week and this guy had a shirt and it had the speed of light in it. I thought that was kind of a bit funny. But it's something that we all know from an early age. The speed of light in a vacuum is c, and we know that you can't travel faster than the speed of light, and we know that you can't send information faster than the speed of light, although people still talk about that. But there's nothing wrong with slowing light down. And so this has been a topic of real interest for a while, and there was a very exciting publication in 1999 that really kind of got the whole community excited about this field when Lena Howell, then at Harvard, reported light speed reduction to 17 meters per second in an ultra-cold atomic gas. So what she'd done is generated a cold atomic gas, microkelvins, in her lab, and she got a laser beam, sent the laser beam into this gas, At a certain frequency, the gas has a very strong and narrow band resonance. The light is absorbed and it sits in the medium and then is emitted quite a time later. And she said, well, what I've done is I've slowed the light down. And she worked out, given the length of the device, that it had been slowed down to 17 meters per second. This was published in Nature, and a short time later, the New York Times reported that scientists had put the brakes on light, and the notion that light had been slowed down to bicycle speed hit the media and generated major waves around the world, and people thought this was just absolutely amazing. What does it mean? Can we harness this? Can we control light? Can we store light down? What's going on here? So, well, the problem, let's just stop. The problem with this approach, I mean, in terms of usefulness, there are a couple of fundamental problems with what was reported here. Anyone want to have a go at guessing what that was? Yes?
The light constantly absorbed and re-emitted may go in different directions than the one intended.
Good comment, maybe. Probably, but there are some other even more fundamental problems. Yes?
It would save huge amounts of energy to keep something that cold.
Yes, I mean, microkelvins is not really compatible with my iPhone. I mean, I've got my BlackBerry, and then I've got this massive laboratory, $1 million lab, and I'm cooling this gas down to microkelvin. So that's one problem. The other problem was its narrow bandwidth. It was limited to an incredibly narrow range of frequencies, and we're talking about terabits per second, terahertz of bandwidth. So what our research has been exploring is we want to slow light down in a resonant structure, but a photonic resonance. And we're going to use photonic crystals, Bragg gratings. I'll explain more of what they are. We can get broadband operation, gigahertz of bandwidth, maybe even terahertz of bandwidth, compatible with telecom, room temperature on a chip. Okay? So, you know, the mind boggles. So what are we going to talk about? These beautiful nanostructures. This is a nice little review paper that my ex-student and I wrote a number of years ago in Nature, talking about the potential for slow light to speed up the internet. I find that an interesting concept. Maybe we can use slow light in our optical signal processing to speed up, to make the internet faster. So what this is all about is photonic crystals. And now, usually this is what undergraduate students get introduced to in second year, and I'm just going to have to do my best with you. But these are materials in which the refractive index varies periodically. So a good example of a photonic crystal is simply a grating that the refractive index varies periodically. It goes up, down, up, down, up, down, up, down. But importantly, the length here is about half a wavelength. So the idea is that light that comes in resonates inside these little mirrors and either goes back or it resonates inside the mirrors and it makes its way through. We know how to make these. We've been doing this for decades, and we can make these not only in 1 dimension, 2 dimensions, and even 3 dimensions. So the best example of a photonic crystal is simply what we call a Bragg grating, a grating structure. I mean, the jargon here shouldn't be that hard. Grating kind of implies something that's a grating. That's exactly what it is. Or a thin film stack. We make these routinely. That's a good example of a photonic crystal. We make these now in exotic optical fibers. We call them photonic crystal fibers or microstructured optical fibers. These are one of the hottest areas of modern physics. These fibers have little tiny holes that have been drilled into them, and they trap the light, not by total internal reflection, but they trap light because of this scattering off these little holes. And we make them on circuits. We drill holes in our little circuits. So where's my chip? Okay, there is not a photonic crystal on that chip. You can't see one, but I could show you a similar chip where there would be tens of thousands of holes etched into it. You wouldn't be able to resolve the holes, mind you, with your eye. We can make these structures in 3 dimensions. Very hard to do. And they occur in nature. This is a fascinating idea. There are groups around the world that have been looking at photonic crystals in nature. In butterflies, in caterpillars, they provide colouring. The scattering of this periodic structure provides camouflage for animals that live under the ocean. So photonic crystals appear in nature, and I'll make a comment because you heard about the metamaterials from Pendry. Metamaterials don't occur in nature. It's interesting, there's a bit of a debate at the moment. Will we see metamaterials? Do they occur naturally? Metamaterials probably don't, photonic crystals do. They come just out of evolution. Evolution leads to these beautiful structures on the back of butterfly wings and so forth. They are photonic crystals. So what I'm going to show you, and this is a simple cartoon, is that in one of these photonic crystals or Bragg gratings, I can slow light down. And it's a very simple picture, but let's see what happens. The pulse of light will slow down. The reason it slows down is actually really simple. The light pulse comes in, it bounces back and forth off these little mirrors. It's rattling around. Tiny little mirrors. But eventually the pulse, if it's tuned to the right frequency, moves along through the grating and it tunnels through to the other side. Okay? We can do that. We do it routinely. We can slow light down. Why is that important? Well, if we can slow light down, we can enhance the light-matter interaction. We can actually enhance the optical nonlinearity because the light is bouncing back and forth hundreds of times across the atoms. So the interaction between the light field and the electron cloud that we talked about is enhanced because the light is bouncing back and forth and back and forth and back and forth. So I can now make ultra-compact devices, very small devices. I can make energy-efficient signal processing devices. Okay? I might pause here and allow any comments or questions, because that's probably hard. Yes?
When making increasingly small structures to do these, to affect properties of light, won't you eventually run into the limits of photolithography when you're printing these small structures?
Good question. So what are the limits of lithography? Well, there are 2 approaches. In the electronics industry, they use photolithography. They design a mask. They take an ultraviolet lamp and they expose through the mask, it's a shadowing effect, onto a photoresist. Then they do etching. So the mask defines the feature size. So the limit of resolution is simply the limit of the diffraction limit of the laser beam that you're using. And there's a well-known equation for that. How do you shrink the diffraction limit? You go to shorter wavelengths. So it's well known, I can reduce the feature size in photolithography by going to shorter and shorter wavelengths. So if you talk to Intel, what wavelength do you think they use in their photolithography?
X-rays.
Almost. Deep UV. Deep UV, 193 nanometers, 100 nanometers. And there is a form of lithography that's called LIGO or LIGA. I can't remember the acronym, which is actually using X-rays generated from a synchrotron to do lithography, and the X-rays give you this incredible resolution to define these very small and very high aspect ratio holes. But in the electronics industry, they're already achieving 50 to 100 nanometer feature size. We're getting close to that. We're not using photolithography. We're using electron beam lithography. We're using electrons. So at the moment, our photonic crystals are fabricated using an electron beam lithography system. Rather than light, we use electrons that are focused much smaller feature size, down to 5 nanometers. But the problem is, it's not scalable. We can't manufacture using electron beam lithography. The photolithography that Intel uses, I can print thousands of circuits in one run. That's why this is so cheap. Electron beam lithography, I've got to go to this $5 million system, and it has to drill one hole at a time. It takes an hour. Great for research. So, good question. So we're waiting for Intel's roadmap to get to a point which is only about a factor of 2 away from where we are now. Then we can mass produce these. Excellent question. There was a question up the back.
So I understand the light we use is about a wavelength of 1.5 micrometers.
Yep.
And normal atoms have an electron cloud that is maybe 1 to 2 angstroms. So how does the light interact with the electron cloud? The electron cloud is so much smaller than the wavelength.
Yes, so the light field is this oscillating electric field. The atom's sitting here. Doesn't matter, the light field comes in, the electric field will still see the atom for sure. And so what will happen is that electric field comes in, bang, the first part of the electric field will see the atom, and then it will start to affect the electron cloud. But then the electron field will come in, and that interaction will start to kick in. But even though the wavelength of light is long, there's an electric field between, it's continuous, isn't it? The electric field is this. You're right, the atom's tiny and the electric field is this big thing. It's like a little guy sitting in the ocean with these big long waves. Okay, and he's sitting there and he's waiting for these big waves. He still gets hit right up in the air, doesn't he? The waves he doesn't get ignored, does he?
But how does it make it different from just like regular optics, where when the light is propagating through the material, that will happen anyway, right?
Here, the point of nonlinear optics is that the light field is strong enough that it's perturbing the electric cloud. Okay. So by definition, it's nonlinear. So it depends on the intensity of the light. So what I haven't really explained is that the materials we use are very special materials that allow this interaction to occur at reasonably low power levels. There was one other quick question. Yes?
My question is that when you slow down light, will you also lose the amplification of it? So wouldn't you make it lose the energy?
No.
No?
Not necessarily. Why would I do that?
As in, if it travels a longer distance, that means it will end up losing more energy within it.
Why? I mean, there's an assumption in your question. Indeed, if this is a lossy material, the slow light will increase the loss. If there is some absorption in the material, when the light's bouncing back and forth, I'm going to get more absorption. If that's what you're asking, that's spot on. And so the challenge is we need to make sure that by the end of the device, we're not killed by absorption. But we can. We get it to work. We do. Yes, there was one other quick question. I've got... No, you're gone? History? Okay. So, now I'm not going to have the time to go through all of the beautiful stuff we're doing, but I'll give you a few examples of what we've done, and then I'll wrap up. But we've demonstrated really convincingly that we can do very efficient, ultra-fast signal processing in very small devices. We reported earlier this year the world's fastest optical switch at 160 gigabit per second, 100 microns in length, okay? Using a slow light photonic crystal. So a little bit more, you have now the idea that Moore's law that we've talked about can go even further if we can make photonic circuits out of photonic crystals. We can build the entire circuit simply by drilling holes, thousands, tens of thousands of holes into this substrate. These structures are difficult to make. The early seminal experiments were basically done at microwave frequencies. Remember I said that earlier, by drilling holes into blocks of aluminium. Okay, and doing measurements with microwave frequencies. And now we use lithographic techniques. We also use self-assembly to create these beautiful structures. So in chemistry departments, people are using colloidal silica to self-assemble these beautiful photonic crystals. So this is an example of my work, and I'm just giving you the scale here because we're going to go into a close-up. This is 20 microns, so this is about 50 microns, 50 microns. Let's work out how many holes are there. There's probably 100 holes, so probably 10,000 holes. Each hole has been drilled using electron beam lithography. It's taken a few hours. So let's go closer. You'll see a bit of granularity. Ignore it. That's just a metallic film that's put on for the imaging. But these are atomically smooth structures. Absolutely beautiful. Ignore the granularity. Now you can see that we've removed a row of holes. So we've created a channel for light to propagate along. And it's in that channel that the light will be slowed down. That's where we will get this enhanced light-matter interaction. So, okay, you can also make structures, as I said, by self-assembly. This was state-of-the-art a number of years ago. Three-dimensional, self-assembling little microspheres in a beaker, and then removing the material by etching, and you end up with these beautiful, absolutely stunning structures that people have used in science. The problem is with self-assembly is how do you define structure and circuits? How do you actually build something useful into their structure? It sort of relies on the forces of nature to self-assemble. So let me wrap up and just give you a couple of examples, and then I'll let time for some questions. This was a big breakthrough. We reported in Nature Physics in 2006 that we slowed light down in a grating structure. This was the record at the time. You can see on the left experiment and simulation. You can see the pulse of light that's propagating at C on n, and you can see the pulse that's been slowed down. Now it's amazing to look at this. This is the record, but we've only slowed pulses of light down by about 3 or 4 pulse widths. Okay? This pulse is delayed by about 3 or 4 pulse widths compared to the pulse that is propagating at the speed of light. So that's far from what Intel's routers do, where they can store data for maybe a microsecond. But it is the record, and it generated some real waves in the field and beautiful physics. Slow waves. I'll give you another example and then I'll wrap up. This was also a big publication. This is one of our photonic crystals. This is in silicon. So this is the same silicon that we use in microelectronics. This is a membrane. It's about 0.5 micron thick. There are about 10,000 holes that have been drilled into this membrane. You can see that there's a connection here. So we've got a light pulse going in and a light pulse going out. And what was amazing here is that this was reported in Nature Photonics, which is, by the way, one of the leading international journals. What was discovered here through this nonlinear optic interaction, remember we talked about frequency conversion, what we discovered, and this is a great story because I think discovery is always the best sort of science, what you don't expect, what you didn't anticipate. Bill and Christelle were in the lab doing this experiment, and they were looking at the light pulses coming out of the chip, and out of the corner of their eye they saw this little green light, little flicker of green. And they were initially upset, worried that they had damaged the sample, that this was some type of fuse effect. Ran into my office and said, look, we think we've got something wrong, and we see white light, it might be green. We've got 1.5 micron going in, and we think it's green. What's going on? And my little brain started to sort of churn along and think, well, if it's green and you've got 1.5 microns, there's a factor of 3, isn't there? And that's a well-known nonlinear optical effect. That's called third harmonic generation. You get 3 times omega. But then I stopped and said, but silicon is completely opaque and invisible. It's like a brick. How are you generating green in this opaque material? Well, the slow light effect, the fact that the light is bouncing around thousands of times in the crystal, it's resonating very strongly. Thousands of times. And then what's happening is it's been scattered out at a very specific angle, directly into your eye, and you can see this green light. And that was just a magnificent discovery that we'd shown silicon was now this versatile photonic material. We could harness slow light to do new physics, new nonlinear optics, and generate these new frequencies. So I'm going to wrap up I've talked about a number of things. In the School of Physics, we're very proud to host a National Centre of Excellence in Photonics. We've got this wonderful logo, and you might recognise the O. What's the O? Say it again? Metamaterial. So I haven't talked about metamaterials because you heard about that from John Penderith, but that's a big part of our program. You can see the focusing of light here. This also represents the 7 universities that collaborate in harmony most of the time. And you also see, if you look very carefully, that it's green. Okay? Very deep. Look, we've done already some amazing things. We've got a vertically integrated program with material science, fabrication, strong theory. I haven't finished. You might recognise this structure here. Gives you an example of the sort of precision we have in creating nanostructures. This is about 10 microns across. You've seen some of this in your tours this week. I'll end by just saying that this is still basic strategic science that we're doing. It's important research. We're one of the leading research groups around the world. The University of Sydney ranks in the top 5 internationally, up with Stanford, Harvard, and other groups. Our research is starting to translate into the real world. We're working with companies in Sydney and overseas. There are some important applications beyond just traditional communications and social networking and the internet, in terms of e-health, e-education, defence, of course, and astrophotonics. We're working with our colleagues in the school in astronomy. And I'll end there with a photo. This is the group, my group. This is the centre. So this is the 7 universities getting together. This is me looking very healthy down on the south coast. And you might recognise my colleague, Professor Martin de Sturkey, and there are some other famous Australians in here and other famous international people. I'll end there, and I'm happy to take some more questions. Thanks very much.